Welcome to the Running Apache Spark Jobs Cheaper While Maximizing Performance presentation. My name is Brad Caffey. I'm a staff data engineer and I work at Expedia Group. Before we begin, I want to tell you a little bit about myself. I've worked at Expedia Group for about 5.5 years now. I work on the Destination Attribute Store team. Our team is one of the largest data producing teams at the company outside of the data warehouse. We process and produce about 25 terabytes of data every day. As you can imagine, our cloud spending costs are pretty high. About 2.5 years ago, I started studying Spark tuning. When my manager found out, he asked me to find a way to lower cost. So I did. I used our department ETL's batch Spark jobs as guinea pigs to find a way to lower cost. And to be honest, I spent a lot of Expedia's money in the process of figuring out this strategy. But the good news is that it paid off. One of the jobs I tuned was this one. This job processed 4 terabytes of data and ran for 2 hours. But after cost tuning, I was able to cut cloud spending by 60%. Now, how did I do this? Now, before I get into how I did this, I want to cover the Spark Executor model briefly for the non-data engineers who are watching. So, when a data engineer submits a Spark job, it runs on a cluster, and a cluster has multiple nodes. In this case, we have 4 nodes running on our cluster. The data engineer has specified to run with 12 executors. And if we look closely at the executor, you can see that you can specify the number of cores to run. In this case, we're using 5 cores. The Spark cores are the fundamental unit of processing power. And in this case, we have 60 Spark cores running. You can also specify how much memory each executor runs with. And there's always a driver that coordinates all the executors that are running. And you can specify how much memory that driver has. Now, the key to cloud spending efficiency depends on the ratio between Spark cores and node CPUs. So, for example, if we have a node that has 10 CPUs on it, but there's only 6 Spark cores running, then that leaves 4 Spark cores that are not being used, even though you're paying for them. This is inefficient cloud spending. Now, the other extreme is if you had 15 Spark cores running on that same node. In this case, you have time slicing happening. Time slicing is when you have 15 Spark cores, or you have more Spark cores running than CPUs available. That means the Spark cores have to compete with overworked CPUs, which slows down processing and is not very efficient. What we're trying to strive for is a 1-to-1 ratio between Spark cores and node CPUs. We want this because AWS charges on a per node per second basis. Now let's go back to that original example. The job before cost tuning was running on 67 nodes because it was only utilizing a third of the CPUs on each node. After cost tuning, I was able to squeeze that same number of Spark cores into just 27 nodes. When running the same number of Spark cores on fewer nodes, that leads to lower job cost. Now, it sounds good in theory, but does it really work? Let's take a look at some real-world cost tuning examples. So in this first example, we have an executor that is only 4 gigabytes in size, running on a node with 128 gigabytes of memory. So in this example, we're going to have about 16 executors running on each node, which means there'll be 32 Spark cores overutilizing 15 available CPUs. So there's a lot of time slicing happening here. After cost tuning, The runtime improved a lot, and the job costs improved even more. In our next example, we're going to have just 8 Spark cores underutilizing 15 available CPUs. After cost tuning, we're able to reduce runtime and improve job cost. Now in our final example, we only have 6 Spark cores underutilizing 31 available CPUs. After cost tuning, we weren't able to get a 1-to-1 ratio between cores and CPUs, but we were able to improve because now we have 20 Spark cores underutilizing 31. Now the runtime did slow down, but the job cost improved dramatically. Now, how did I choose the Spark parameters for cost tuning? Simple. I used the cost-efficient executor configuration as my model. Now, the cost-efficient executor configuration uses all node CPUs without time slicing. Now, the configuration will vary depending on which node you're using. So let's walk through the steps to determine the cost-efficient executor for this node that has 16 CPUs and 128 gigabytes of memory. So the first thing you do is you set aside 1 CPU for the cluster manager, which will leave us with, in this case, 15 available CPUs for processing. With 15 CPUs available, that means there are 4 possible executor configurations. 1 executor with 15 cores, 15 executors with 1 core, 5 executors with 3 cores, and 3 executors with 5 cores. Now let's walk through each of these and see which one will be the best. Now, when you have 1 executor with a lot of cores, it tends to have a large amount of memory, which can lead to garbage collection delays. Executor memory should never be more than 64 gigabytes. So for this reason, we're going to rule out a single executor. Now, with 15 executors, you have to keep in mind that executors are designed for parallelism. In other words, they're designed to work with multiple cores at a time. To enable this parallelism, Yarn adds memory overhead to executor. When executors only have a single core, memory overhead doesn't add much value. It essentially becomes bloatware. And memory overhead for single core executors can be really difficult to tune. Because when you have 15 executors and overhead on top of that, that's a lot of memory being devoted to memory overhead on your node. Which means you need to get it just right in order to maximize the amount of memory that's available for your executor, which is really difficult to do. So for that reason, we're going to rule out 15 executors as well. So now that leaves us with 3 executors or 5 executors. An executor with 5 cores is preferable for 2 reasons. The consensus in the Spark tuning community is that 5 core executors have been shown to be the most efficient at parallel processing. And from my own experience, I found that 5 core executors perform better than 4 core, 6 core, 3 core, and 7 core executors. Also, having 3 executors per node means less memory overhead is being consumed on your node, which means you have more memory available to your executors. So we're going to rule out 5 executors per node. Now that we know how many executors will be on a node, we can determine how much memory each executor will have. So we know that this node will have 128 gigabytes available. However, not all that node memory will be available for the executors. To determine the available memory, we must look at the cluster log. Now in this case, we're looking at the application log in Yarn, and it's showing that the available node memory is 112 gigabytes. So that means there's 16 gigabytes of memory reserved by the cluster manager and system resources. So that means we have 112 available for the executors. So now, to determine the memory per executor, we simply take the available node memory and divide by the number of executors, which gets us 37 gigabytes. But remember, this 37 gigabytes includes memory overhead. So we have to back out memory overhead to know how much memory we request for the executor. Now, Spark defaults memory overhead to be 10% of your executor memory size. So what we do is we divide the 37 by 1.1, which gets us 33.6. And then we can round down to 33. Now, on some platforms, like Qball, there is a fixed memory overhead. In that case, you just simply subtract the fixed memory overhead from the total memory to get memory for the executor, which in this case will be 34.7, which rounds down to 34. So that means 34 or 33 is the recommended memory size for executors running on this node. Now, let's talk about executor count. Remember, our goal is to utilize all available CPUs for every node, which means we'll want executors in multiples of 3. But we have to remember that the driver also gets loaded onto our nodes, which in multiples of 3 would mean that the driver will be on a node all by itself, which is not efficient cloud spending. So what we need to do is we need to leave room on one of our nodes for the driver. So we subtract 1 from a multiple of 3. Now, with this count, every incremental node adds 15 cores of processing power, which is very cloud spending efficient. Now, let's look how much memory we reserve for the driver. AWS recommends sizing your driver to be the same size as your executor. And here's why. If you have executors that are 34 gigabytes, but your driver is only 20 gigabytes, that means you have room on your node for other executors to be added, which means another job could add an executor, which would cause time slicing with your job. So we don't want that. So in order to do that, we size the driver to be the same as the executor. So this means that the cost-efficient executor configuration recommended for this node will look like this. I do realize that not all data jobs are the same. Some need more memory, some need less. So what I'm recommending is that you always start with this cost-efficient configuration. And if errors happen, then modify to accommodate those errors, to make it work. And I will provide resources at the end of this presentation for what to do in those scenarios. Now, how can you tell if your cost-efficient configuration is running cheaper? All you got to do is look at the job costs. Let's figure out how to determine them. Now, determining actual job costs is actually pretty complicated to do manually. At Expedia Group, we actually have pipelines that combine AWS hourly cost data with Qball daily cost allocation files to get actual cost. Now, if you don't have a pipeline like that, and you're an EMR user, you can use Cost Explorer. And if you're a Qball user, you can use Big Data Cost Explorer. So let's break down the cost that AWS charges for a Spark job. So the biggest cost is by far going to be the EC2 instance cost, the cost of our nodes, which is what this presentation is focused on. You can also be charged for EBS volume costs. Now, this is a charge for persisting data to EBS volumes on your cluster during a Spark job. Now, what that means, now I'm not talking about you saving data to S3 during your job or at the end of your job. What I'm talking about is when you're persisting data during your job so that you don't have to rerun a data frame or a SQL query. The persisting of a data frame to an EBS volume will cost money, and it'll be cost for how long it's charged. Another cost is data transfer cost. Anytime you transfer data out of an AWS region, you will get a charge. So if you're transferring from one region to another, that will cost you money. Or if you're transferring data out of a region to your infrastructure, that will also be a charge. It's always free to load data into AWS or to operate on data within AWS. And then finally, every data management platform charges a slight overhead. Qball, EMR, Databricks, they all do that. Now, what if you can't get actual cost? That's okay. We can estimate cost. And true story, I developed this entire cost tuning strategy just from estimating cost. It was only earlier this year that I got a hold of the actual cost data shown that I was able to confirm the strategy really does work. So this cost estimate method will work if you don't have actual cost data. The first thing you do is you need to determine how many executors will fit on a node by dividing the available node memory by the total executor memory size. Remember to include that memory overhead. Then you determine the EC2 cost for your node type by looking at the AWS EC2 instance pricing page. Then determine how many nodes the requested number of executors will fit on. Once you have those figures, it's simply a matter of multiplying the node counts times the node cost by the runtime. And then that will get you the estimated cost value. Now, I do have one disclaimer. You must disable dynamic allocation for this estimate method to work. As we all know, with dynamic allocation, the number of nodes used during your run can change, can increase or decrease, which will throw off this estimate value. So whenever you're cost tuning, just disable your job for your before cost and then run it again with your new parameters for your after cost. And then once you've settled on Spark parameters that work for you, then you can enable dynamic allocation again to save even more money. And I also want to point out that the purpose of estimating costs is really to track the relative changes in cost while cost tuning. So the figures you may get may differ from actual cost values. That's fine. All we're trying to track is the relative changes, because what you're doing is you're changing the two variables that you have control over: the node count and the runtime. Fewer nodes, the same runtime, equals lower cost. And I also want to point out that even if a job runs longer, it can still run cheaper. Like for example, if this job took an hour to run but only ran on 2 nodes, that's significantly cheaper. So just keep that in mind. In summary, remember that we're trying to utilize all the node CPUs so that we can maximize our cloud's spending dollars. Use the cost-efficient executor configuration as a guide for your tuning Spark jobs. Use either actual or estimate costs to determine if the cost tuning is working for you. Now, if you want to learn more, this presentation covers the first 3 parts of my 6-part blog series on the Expedia Group tech blog. You can find this blog by just Googling cost-efficient executor. Part 4 covers how to migrate existing Spark jobs to the cost-efficient configuration. And in there, it also tells you what to try if a migrated job runs slower. Part 5 covers tips for resolving common errors when switching to the cost-efficient configuration. And Part 6 summarizes the entire cost tuning strategy and includes an FAQ. So that's it for my presentation. Thank you so much for watching. If you have any questions, please reach out to me on my blogs. I like people to post questions there so that if anyone else has the same question, they can see that question and the answer. But please let me know, and I'd be happy to help you. Thank you very much.